Hello, everyone. Welcome to the event today, and thank you for joining us. My name is Joe Kubasek. I'm with Cimquest, and we're going to be hosting today's event, which is called Breaking the Mold: Xact Metal for Tooling. First, let me take a minute, and I think we're going to run over there we go, for the agenda. So we're going to do a brief introduction, and then we're going to talk about what is tooling and the applications, Xact Metal's capabilities, and so on, the ROI, as well as thinking differently. And then at the end, after Scott is done, we're going to have a Q&A. So if you want to hold your questions to the end, or if you need to, please put them in the chat area, and then we'll be able to accumulate those so we don't forget them. So Scott, you want to put on the next screen for a moment? So let me just take a minute and tell you a little bit about Cimquest. We are a provider of hardware, software, and training solutions for manufacturing products, and we support every step of the way. Next screen. So Cimquest has been around for 34 years, and today we service the Northeast, the Mid-Atlantic, and the Midwest regions. We are 70 employees plus strong. We have our headquarters, which you see right there, in Branchburg, New Jersey, and then we have satellite offices in some of the different parts or different regions. Next screen. So Cimquest is a reseller of a value-added reseller, and we provide reseller services for Mastercam's CNC programming software, for metal, plastic, and ceramic 3D printers for both professional and the industrial applications areas. And our 3D scanning and reverse engineering team also has hardware and software solutions and provides that service as an outsourcing service right there in our headquarters area. Next screen. So because we're a value-added reseller, we provide solutions and not just products. And that means that we provide you with end-to-end support for all of your manufacturing projects. And as you can see from that little screen, it's touching on all the areas that help to support your projects. So as I said, we're not just selling you a product, we're providing you with a solution. Next screen. But today we're here to talk about 3D printing. Go ahead, next one. So we provide, there are a wide variety of 3D printing technologies, and we provide some of the very, very best. We provide all of the solutions that would help you in the marketplace. Things like resin or extrusion, binder jetting, as well as powder jet fusion. Next screen. And Cimquest provides the very, very best in all of these technologies. But today, we're here to talk with Xact Metal 3D printing. Scott, next screen. One of the most important things to remember about 3D printing is that it's not just about the printer, but it's about the application that you need to print. So typically, those applications are going to fall into one of the 5 areas you see: concept modeling, functional prototypes, manufacturing tools or jigs, fixtures, tools, end-use parts, and now production. Next screen. Now today, once again, we're introducing Scott Kramer, and Scott's with Xact Metal 3D printing. At the end, as I said, we're going to have questions and answers, or you can put them in the chat so that we address them. So take it away, Scott.
Thank you, Joe, and thank you, Cimquest, for all the work you've done and being an excellent partner. Couldn't ask for a better solution. It's a really good partnership that we've got together. Hi, everybody. I'm Scott Kramer, as Joe said. Been around the industry a long time. You can see here, this is probably about half the companies I've worked for, sad to say, but in the same light, it shows that I have done a lot of things over the years, right? So 33 going on 34 years in the industry. I've worked at some high name that you recognize here: Ford, Carbon, PTI Engineered Plastics, right? I've also, around 2018, I kind of delve off the injection molding world and headlong into additive manufacturing, where I spent time at Carbon, Velo 3D, Mantle, and over here at Xact Metal, and I'll kind of cover all that. So I went into, actually, I'll start to go into here. So where it all started. So back in 2010, I printed a mold insert there. You can see that's in plastic, not the best solution, but it'll make sense here in a minute. We were actually molding 33% glass-filled nylon parts, right, for structural integrity. But I printed a mold insert. I worked with a guy that developed this interesting technology, something a little out of the norm. We printed the mold insert, and we got like 5 shots out of it, right? But so it didn't really last a whole long time, especially with the glass-filled nylon. But the idea was that I realized there's potential here, right? Fast forward a little bit, around 2012, we started to secure our first metal AM machine when I was at PTR Engineered Plastics. And you can see once we got our first machine, it was laser powder bed fusion. Around 2016, so after about 3.5 years of having the technology, we started really pushing the boundaries of what can be done. So what you're seeing here, the insert on the right, I'll dig into a little bit later, but it's about a 3-inch diameter, about 7 inches tall, and it's completely hollow. The idea was that the way people are trying to adapt metal AM to the existing technology or to existing ways of plastic injection molding today is kind of like they're saying, okay, there's this new technology and here's an old way of doing it, and we're just going to kind of like adopt it, put conformal cooling in it, and call it 3D printed, right? Which is not wrong, but at the same light, if you start thinking about this thing differently, you can actually open up the industry a bit more and start to kind of open minds hopefully a little bit. So I'll cover into some of the lightweighting and stuff a little bit later. I do want to point out what we're involved in. I'll get into our technology and get into all these case studies. We're heavily involved in women in 3D printing. We're members of MAP, the Manufacturers Association for Plastic Processors. We're members of AMT. We're members of America Makes, members of SME, and also members of American Mold Builders Association. Industry challenge. So the biggest, I'd say there's a few challenges here, and I'll cover some of that. But I think the biggest challenge everybody has is the high cost of acquisition to get metal AM into your shop. Let alone the fact that I have to train somebody special to do this thing. I have to hire a special additive manufacturing specialist, or whatever the case is. But I really want to point out the third bullet here is the one button theory expectancy. I can't tell you how many people I talk to that go, I could just hit that. What is it? Staples has that little red easy button, right? You just hit that, tap that easy button, and boom, I've got one part, one solution, and it's good to go. And it's not the case, right? There's other technologies that are out there. I've seen a lot of the metal AM. I still have NDAs signed with 3 companies that are still not even public yet, trying to help them develop their technology. But the point I want to try to make is that there is no one button solution yet. A lot of companies are getting close. You're still going to have to do something as a secondary operation. You're still going to do some spotting of the tool. I haven't seen anybody that can go right into, fully in yet. You're still going to either spot the tool, you're still going to do some threading, you're still going to do some tapping, you're still going to do some grinding around the outside or some finishing, some profile around the outside. You're always going to touch something in some way. So the thought was that if you had an affordable option that could get you there faster, then that's where this solution can come in. Now, I do want to talk about what our technology is. It is laser powder bed fusion. So metal powder bed fusion, laser powder bed fusion, DMLS, everybody's got all these different terminologies out there depending on what company you work for. But basically, we're laying down powder in layers of anywhere from 20 microns to 100 microns thick. For those not familiar with microns, it's about 8 thou to about 1 thou thick layers. And then we come in with a galvanometer and we actually laser weld all that powder together. So pretty simple, right? In a sense, it's a laser welder, right? We're welding powder. Build times range from anywhere from 2 hours to 24 hours. And you can do single laser, dual laser, and I'll cover some of that here in a minute. Basically, what we've done is we've developed a new level of price and performance in metal AM that allows companies to decentralize, basically a decentralization of the technology for large organizations. So small companies, mid-sized companies, larger companies, it allows them to easily adopt metal AM. So you can see here the picture on the top right, the Model T. Everybody remembers that? I don't know how many people are going to remember that, but the story behind it, right? So Henry Ford wanted the Model T to be an affordable, simple to operate, and durable, right? And Xact Metal is a similar model. We're trying to we've developed a machine that's also affordable, simple to operate, and very durable as well. So our capabilities, we can do, everybody always asks, can you do conformal cooling? We can do conformal cooling. We've got a really good surface finish. I'll touch on those. The tolerances, I'll touch on that, and materials as well. as we start to go through this. But I do want to point out that this is laser, I mentioned before, laser powder bed fusion. This is not sintering. So you don't need to sinter something as a secondary operation in order to achieve your final part. What you print is what you get. So a little bit of history here. We started off what was called the XM200C. So it was about 125 cubic build volume. It was with an XY gantry system, so kind of like a lift top. Great lower barrier of entry for a lot of companies. We introduced that around 2018. But around 2022, we developed what was called the 200G. We released it into the market, and you can get it in 150, 150, 150 cube build volume. You can get single laser, dual laser, 100 watt, 200 watt, 400 watt. Basically, we build the machine to whatever the spec is going to be for that person, right? We've got quite a few options you could choose from. The nice thing is your price range is anywhere from 110 at a lower end for the 100 watt system, all the way up to a dual 400 watt system, getting up around the 250 grand price range. Materials offered. This is a big one. So this I'm kind of excited about. So the M300, the margin steel, which is kind of like, I'll call it like the vanilla of the industry, right? It's something that everybody uses. They've been doing it for 20 plus years, right? I think going on 30 years now. It's good material. It's really good, but it tends to corrode, right? I've got parts sitting on my desk that, it's humid where I'm at, and the day you print it, it starts rusting that day, right? So, but all steel rusts for that matter, unless you get into something like what we do with Cor-x with our new partnership with Udahome, and I'll cover that here in a little bit. And also want to note, coming soon, tooling steel. We've got a couple other tooling steel companies we're working with as well to bring more tooling to the industry. And I think that's where part of the gap is. Besides, I mentioned about the one button theory and the price point for this thing. I think tooling steel is another big gap in this industry. That okay, you can do margin steel. It's kind of like a material that just kind of thrown out and saying, hey, this is kind of like a catch-all material that can do stuff. I'm not knocking it. It's very good. But I think that for more mold shops or other industries to really adopt it, we really need more tooling steel options. And that's what we're here trying to do. The first being this Cor-x material from Udahome, and a few others that will be coming down the road here later on. But the great thing is with our machine, it's not just for molds. You can do bend over arm tooling, fixtures, gauges, all kinds of stuff. I'll cover some of that, but you can see here the different materials listed. We can do 316L, 17.4, 15.5, 420 variations. We can do Inconel, cobalt chrome, which we do for the dental industry as well, so we can get some very fine detail. We have copper alloys, bronze. We could do gold and silver. You could do aluminum alloys and titanium alloys. So let me get into so this is a slide that Udahome put out at the ICAM 2023, but I thought it was just kind of like a great thing, like what is a tool? Most everybody here already knows what a tool is. That's probably why you're attending, so thank you for that. But just kind of like just trying to set the idea that my background is plastic injection molding. I've done some extrusion, forming tools, die casting, actually not die casting, but trimming tools, engraving tools, sheet metal prog dies and whatnot. But in a nutshell, tooling is a very broad term, right? It can be anywhere from making cutters to extrusion to plastic injection molding to stampings. And pretty much metal AM could be used for all these technologies, right? Die casting has already adopted it. However, the heat bed requirements are a bit higher than what a lot of other companies can actually handle. But there are materials for all of this stuff. And I think we're on the verge of more and more people starting to adopt it. Because we're starting to see where the future is going to go. Tolerance of printed parts. Everybody's going, hey, what's your tolerance, right? I want to make sure we cover that. So parts that are about like 1 inch and 3/16, we can hold about 2 thou tolerance, plus or minus 2 thou over 1 inch and 3/16, or about 30 millimeters. 60 microns over about 30 millimeters. Beyond that, we have what's called everybody's got this ratio figure. It's a 0.2% tolerance for every 30 millimeters beyond that. But I do want to note that there's a couple parts here I'll cover. We've had parts that were 3 inches by 3 inches, or about 76 mils by 76 mils, that were held within 2 thou tolerance over that 3 inches. So it's pretty good tolerancing. The one thing that our machine is it's adjustable. It's not like a said and done kind of thing. You can go in, you can fine tune the laser, you can fine tune the surface layers that you build at, you can fine tune the laser wattage. You can fine tune certain surfaces that you want to do certain things. It's really much more accessible for everybody to be able to kind of tailor to their own. Minimum wall stock, you can see down here, we can do stuff at 100 microns thick or about 4th thou thick. Not that you're going to be molding over walls that are 4th thou thick, but just the idea that for printing parts itself, you can get some very fine detail with it. Minimal practical hole size, 200 microns, about 8 thou. I actually have a part that, a little sample in that we put in our boot that there's a 4 thou hole going through it, and you actually have to hold up the light in order to see through it. So we can get some very fine detail with this technology. So industry standard surface finish. What is a surface finish, right? So everybody's already used to seeing this, right? The typical, if you see this part here on the right, the upper arrow, you can see that's an EDM finish. That's typically right around a 3 micron RA. Yes, I know if you did, if you add some slurry, you could probably get it down to about a 1 micron RA or a 2 micron RA with a better EDM finish. There are those options out there. I know that, but just as a rough standard, what you're going to get when you order something through other sources online or other mold shops, it's right around a 3. And the lower portion here, you can see the lower arrow. That machine surface there is a 0.8 micron RA. Now, granted, that was used with a ball cutter. I probably would have end milled it to get a little better surface finish on it. You can get it down to more like maybe a 0.4 micron RA. But again, this is just trying to stress that there's a certain finish that the industry is used to seeing. And they just assume that when I hit a 3D machine, a 3D metal printer, and I hit that button, that I'm going to get these surface finishes out of it. It's not the case, right? But you're going to get close. So what we've done here is, again, as I mentioned about our machine can be adjusted or tailored or fine-tuned. We've printed this insert here you see on the top right. Again, that's that 3x3 insert I was mentioned earlier where we held 2 thou tolerance over the whole thing. The initial print at 200 watts with 100 micron, I don't get into kind of down in the weeds here, but it all makes sense. When that part was printed, we were about a 12.5 RA or 12.5 micron RA surface finish on it, which was a bit too rough. So what we did is we refined it, we dialed it back to 100 watts as we got towards the top. So we blew the first inch at 200 watts, then slowed it down, did the final top portion that you see here with 100 watts. And by doing that, we were able to get a 3.3 micron RA surface finish. So much closer to what I was talking earlier in regards to an EDM finish. So it's just a little bit rougher than a standard EDM. Now it's getting it more makes sense where people are like, oh, this is getting really good, right? You got that certain feel that you dial your fingers into as you feel it. On top of that, we're actually currently printing with a 50 micron spot size. So our machine, you can buy it 2 ways. You can get it with 100 micron spot size or 50 micron spot size. And what that means, that's a diameter of the laser that's actually coming down and melting the powder together, or the powders together. So some people will enable this technology because they want to print rough parts quickly with conformal cooling in it and then come back and do a bunch of secondary operations and get prints in hours instead of days. Other people are like, hey, I want a little more fine detail in certain areas, and that's where the 50 micron spot size comes in. And if you want to switch between the two, you can do that as well. It's a little adapter kit to swap out the lens, but you're able to do that as well. I do want to point out that the M300, the margin steel with benching, can achieve an A2 finish. So a lot of your medical molding, your clear blue polycarb parts, well within the surface requirements for that with the benching. Speaking of surface finish, this is a really cool one. Again, I get excited about this kind of stuff, but Udahome Cor-x material that we're printing right now, you can actually achieve an A1 surface finish. Now, that's not right out of the printer. Again, going back to you still need secondary operations, but this stuff, you can see the pictures on the bottom left, you can hand finish it to an A1 surface finish. So this is stuff that they've already proven out, they've already done, and it's real exciting to see because now this opens up opportunities for the lens market, right? So opticals, optical molding, lens molding, like if you look at tail lamps on cars or on motorcycles or UTVs, there's a lot of potential to go after where the designs are limited because of standard drilling, standard waterline drilling processes, right? You can't get quite close enough to that surface, which causes fogging of the surface because it's a hot spot on it. So if you could print those optical mold inserts with a material that allows you to get an A1 surface finish and give you the corrosion resistance, that's a win-win, right? And it's something that nobody else has been addressing. So what I mentioned earlier about making tool steel so more companies can work with materials that they're already working with. A lot of people are already working with Cor-x plate steel itself right now for making mold inserts. So this is just an added capability for those companies. So what is Cor-x? For those that are not familiar with Cor-x, it's a corrosion-resistant grade of steel. And I don't know if anybody can see my cursor or not. Hopefully it's showing up here. Here's Cor-x right here. So if you look on the left side, you've got your corrosion resistance, right? The higher you go up, the more corrosion resistant it is. And on the bottom, the farther right you go, the higher the wear resistance. So to give an idea on Cor-x, here's 17.4, here's 304 and 316 on the left side. So it's very close to a 300 series stainless for corrosion resistance, which is really good because now you don't have to worry about those water lines corroding unless you're pulling water out of the lake like I've seen some people do, unfortunately, in the past, and you're getting all kinds of contaminants in there. That's a whole other story, but work with us. We'll talk to you on that one. And the wear resistance thing, I do want to point out that here's the 420, what a lot of people are used to, and here's Cor-x. So from a wear resistance wise, it's pretty close to a 420 stainless. However, the cool thing about the Cor-x is your thermal shock is better than a 420. So think of it like, let's see, I guess like if you think of it like H13 versus S7, right? So those tooling, so I'm nerding out here on material. So if you look at like S7 is a bit more malleable than an H13, where H13 is a bit more brittle, more tendency to crack. Cor-x is like your S7 in this sense. It's going to be more malleable than a 420 stainless. So it's kind of like almost like the perfect grade of material. It's really cool stuff and exciting. So dig a little bit deeper in here. I'm not going to read all this stuff and bore everybody, put everybody to sleep, but the critical parameters here, you've got your wear resistance and hardness. So for your long run tools or your reinforced plastics or high temperature materials, this is a really good material for it. Your toughness, your crack resistance, it's much better than a 420. Those who have printed 420 parts or had parts printed in 420 steel, you know exactly what I'm talking about. That stuff tends to crack and it really moves on you. It's got a lot of tension inside of it. The corrosion resistance, again, I've already mentioned that. I'm not going to beat that one to death. Cleanliness, you got your surface finish, which you can get, which is the A1 on it, which is really good. And your thermal conductivity help reduce cycle time. It's a really interesting material. And the cool thing is, I keep saying the cool thing. So you can print from scratch, right from nothing, where you've got just our A2 plate and then you build on top of that. Or if you can do what's called, a lot of people call it the hybrid method, where you take an existing Cor-x plate or part of your insert that you've already done with standard drill lines on it, and then you build up on top of that. So you can put just the 3D printed portion where you want it. So I'm going to start covering some case studies here in components, right? Everybody starts looking at molds. Like if you think like I used to do big tools, like what do you call it? Like instrument panels for vehicles, right? And people go, oh yeah, I make these big tools. Your build volume at 6x6 is really going to fit, right? But if you think about it, inside of that large instrument panel, you've got tons of undercut areas, you've got tons of little lifter heads, you've got a lot of dog houses, things of that nature, or hot spots. If you locally inserted little pieces into that, those you can build in a 6x6 volume. Yes, some slides and stuff or lifters will get bigger than that, but the idea is just got to think a little bit differently. So you got your core and cavity inserts you can go after. You have sprue bushings that you can go after, and I'll cover some of those on costs and whatnot later. You've got slides, like down the bottom left here, you've got slide bodies, slide noses. You could still build a slide normal and build a nose on the face of it, 3D print that on top of the face. There's a variety of ways you can do that. Hot drops, that's another big key one people are going after. And then I want to point out lens molding again with the Cor-x being able to go after A1. And you can actually see the picture on the right, that's some electrical connectors, and I'll cover that one here shortly. I'm going to get into one of the case studies. Again, it's at early stages, so we got a whole lot of case studies that are ongoing, but nothing that'll be public. You'll see more of it at NPE in a couple months, so please stop by our booth. But this one here, this actually, I wrote sprue bushing, but it's not actually sprue bushing, so my apologies here. Good things about live talk. So the picture on the left you see is a CAD model. Now this was for a customer making it was a nozzle bit for an epoxy two-part mixture system. So this part here on the left, you can get an idea. It's about 45 mils in diameter. about 116 mils or 114 mils tall. You can see that blue channel in there. Sorry, I'm pointing to the screen. It's not going to help you. So the blue channel in here is actually conformal cooling. The original style was an old Cascade bubbler inside of there, and it just wasn't quite doing it for cycle time. Now, what's interesting about this tool is it was actually a 20-year-old mold. So they didn't have CAD on it. Well, they had some CAD, but they didn't have all the CAD. So what they did was they knew they had a lot of secondary operations they were going to do, right? Again, going back to that one button theory, it's not going to give you this beautiful surface finish on here right out of the printer. So they knew they're going to do secondary operations, but they couldn't do this 3 millimeter diameter water channel any other way. Now notice this is a round water channel. This isn't teardrop shape. This is round. So interesting point. You'll see we've gone up through 6 mil, 7 mil diameter, or 6 mil diameter, being completely round without having a teardrop shape, which is pretty exciting. But this part here, I do want to point out that in 17 hours, we printed 2 of them. Now, they actually had a 4-cavity tool. We could have printed 4 at once. We were just kind of being conservative and printing 2 at a time. But what we did is we added 10,000 stock everywhere, knowing that he's going to go back in and he's going to do all kinds of, he's going to heat treat it, he's got to machine it, he's got to grind it, he's got to EDM it, he's got to polish it. But I do want to point, it's kind of hard to see here on this picture, but on the left side, there's this tiny little vertical hole you see. That's a 20 thou diameter hole that goes halfway through, then opens up bigger for the ejector pin clearance. But the point is that that 20 thou hole was already put in for him for locating as he started to do this, which is down in the bottom of this clip here. So this tool, they reduced the cycle time from about 20 seconds down to about 18 seconds. They took 2 seconds of cycle time out of it. And this is on a 4-cavity tool, which runs 24 hours a day, 5 days a week. Now that they've done this first sample set, they've got about 4 other tools they're going to start to do this with as well to get this reduction in. I do want to highlight one of our new partners, JST, doing mold connectors. They have our machine as well. This is a mold they did with one of their sample parts here. You can see this connector part here. Picture's not very clear, the actual connector part you can see, but these are the 2 printed inserts, cavity and core set. But I want to show why, their speed. They printed the insert to test new product design quickly, so quick iteration. They liked the idea that parts were out of the machine and the secondary operations were all done in about a day and a half. That's really quick for tooling, right? So you're, again, going back to the quick iteration, or you need tooling today, not 6 weeks from now, or a couple weeks from now, you want it in a couple days. This is where the technology really comes into play. Lower cost. So besides getting the parts out quicker, they had lower cost. They were less expensive than traditional. The cost savings that they estimated here were about $34K a year for different various components. That's quite a cost savings, enough that they wanted to bring it in-house because our price point was there, and they can use this for not only printing mold inserts, but as I mentioned before, you got all these material options for our machine, for our technology, but they can do mold inserts, they can do fixtures, they can do jigs, they can do gauges, they can do automation equipment and all kinds of things on their production floor. So it's not just this machine can only do one thing, right? It can do a variety of things, which is really exciting about it. So it makes it an easier sell to the boss to say, hey, I can do this and I can do some other things too around the shop, right? It gets an easier adoption to different corporations. Now, I talked about conformal cooling. I want to step back a little bit and talk about it a little bit deeper here. So for those that are unfamiliar with conformal cooling, I think probably most everybody is, but just in case you're not, the conformal cooling is a way to cool a plastic part during the injection molding process. So the method was developed to remove heat evenly from complex parts. So you can see, again, this part here that you've already saw already, about 3 by 3 by about 1.5 inches tall. You can see there's a lot of up and down geometry through here. And this water line here, this is a 6 mil diameter water line, printed as a diameter, not a teardrop shape. You can see here it's jumping all around inside of this part here to help cool it. This part here on the right, this insert, this is actually printed in Cor-x. That's why it's not rusty. Right? Cool stuff. So inside of all this part geometry, this is actually a button for Volkswagen. It was basically if you look at like your seatbelt in your car, the little button, the little orange button down on the side there, that's what this actually forms, a little button. So there's actually side geometry on here, which actually has to flex to go out to give it pressure inside. So it's actually spring pressure as well. Stuff that couldn't be done with other technologies, but can be done with ours, can be easily printed. So undercuts, overhangs, all that stuff can easily be printed with our technology. But I do want to point out the key points of conformal cooling. You can improve your cycle time. Now, that's only if you design it correctly. So I want to get on my horse, what they call, step on the horse here for a second, or beat this drum here. So I think a big gap in the industry is with the conformal cooling. So there's a lot of, I'm not going to name names or point fingers, but a lot of people will say, hey, I could take this insert and instead of 3 drilled lines, I could do something like I designed here, right? And it's good. It's going to be better than what I had. It's not necessarily the case. I have seen examples where people will design conformal cooling in, and it actually hinders the plastic part. You're actually making a worse plastic part than if you just went with traditional. So I think the cooling analysis portion is key to making this successful. I know people over the years that have had parts done. They're like, oh, the 3D printing's garbage. It doesn't do what it's supposed to do. I made conformal cooling and it didn't work. And it turns out that they just had a bad design, right? So being able to use the softwares like Mold-X 3D really come in handy for being able to accurately do the cooling analysis and make sure that you're doing doing it justice, right? You can reduce your scrap rate. At the end of the day, if it's not doing its job right, it's gonna just kill this industry, in my opinion. And I think that's where there's a gap right now. Sorry, get off my high horse there. I just wanted to make sure everybody understands that. That's a key adoption to this industry is education. Also with conformal cooling, you're going to reduce your scrap rate and then less corrosion with the Cor-x. So that's another big key point why people are afraid to do conformal cooling, because they got these crazy water lines that are all going to rust up and block up, then they can't drill them out and clean them out. So what do? There's processes out there with acid flushing and things like that. DME has a really good system as well, where you're able to kind of flush it and do an ultrasonic in there to break things up. So that does help some, but at the end of the day, if you're printing with material that's going to rust, it's going to rust. You're going to be chasing it down constantly. So now I'm going to get into tooling examples. So this one here, the idea is to look at this and say, hey, this is kind of what I do, right? Obviously, as injection molders, there's some stuff that we kind of do repetitively over and over again, but pretty much everything that comes through is going to be different. So this is here just trying to give a cross section of a variety of different kind of parts. You can see here starting on the left, and actually if you go to NPE, you'll see all these parts in our booth or any other shows that we attend. You'll see those. But the part on the left here is going with the lightweighting theory, right? We could print 4 of those in about 34 hours. It would cost you, if you own the machine on your floor, a 200 watt, 100 micron spot size would cost you about $114 each to make those parts. So if that's all you ever did for a living was just that, your throughput would be about 721 parts a year. The next part over, the one you've already seen, that was about a 17-hour print at the 200 watt, 100 micron spot size. It would cost you $245, again, if you had the machine on your floor. And that includes amortization and labor, gas, electricity, powder, all that stuff's all included in that. There's no other hidden cost that you're going to see above that. Now, granted, every single part you see here requires secondary operation. So I want to beat that horse. You still are going to have to do some sort of secondary operation to it. But if you can get a part printed, kick it off today, and tomorrow morning when you come in, it's ready to go. That's a win-win. The third column over there, you'll see sprue bushings. Those are 5-inch tall sprue bushings. We can print 4 at a time, or I'm sorry, in this case here, we printed 6 at a time. It's about a 48-hour print to make those, to make 6 of them, and they cost about $100 a piece. And I don't know if last time you looked at DME or PCS website, but they go for like $900 or $1,000. So hopefully they're not listening to this right now. Sorry. But anyways, this is what you could do, right? If you want to build a business case out of this, but you can make 767 of those a year. And the picture on the right, it's a small little button for Freightliner we did years ago. The idea is, are you doing big inserts? Are you doing small inserts? Are you doing inserts that are like, 6 by 6 by 6? You're filling up that build volume, right? That's where the 400 watt laser is going to be your friend, because you can build stuff a bit quicker, but it's going to be rougher. You still have to do some secondary operations to it. Or do you want to go with like a dual laser system, where you can do multiple different parts and print them all in a faster time frame and get your throughput much quicker? So if you're building caps and closure stuff, you're making 96 or 128 cavity tools. It's still going to be somewhat of a bottleneck, but you can see the parts here on the right, right? You can print 9 of these in 24 hours. So kick it off at 8 o'clock this morning, 8 o'clock tomorrow morning, you come in, you're cutting all those off. So the throughput would be about 2,300 of those a year. So, and it costs about $40 a piece. That's really good. This is all these prices you see are all with the Cor-x material. I do want to touch off on some of our new tooling partners. As I mentioned before, on the top right, JST, they have our machine, and I believe they got the high-end machine, the 400 watts. They can do a lot of stuff. Atco Tool, they're newly on board tooling. They do tooling and machining. They are another great partner. Going to be let's call it an educational hub based in Meadville. Obviously, Udahome, I've kind of beat that horse, but they're a great partner. They've been around for, I think they're the oldest steel manufacturer in the world at over 400 years. They're actually older than the United States, which is really cool story behind it, but really good company, great partners. Down on the bottom left, you got Mahle. They make pistons. If you're familiar with those for your cars, they are one of the early adopters of our machine, and they were using it to make tooling that didn't exist. So they're making taking the pistons itself and the grooves, and they're actually making little chip makers inside of that by being able to add fluid channels through there to direct the fluid where they need it to go. So they're making tooling that didn't exist before. And the interesting story with them is they've got a lot of senior gentlemen that were not wanting to adopt metal additive because that was going to be the next group's problem, right? The younger kids coming in. But once they started seeing all the different things they could do with it, they became quite large adopter and are printing all kinds of stuff for their shop down at the piston place. I also want to highlight Plastech Group. They're also an early adopter of our technology. Very good company there in Erie, Pennsylvania. They feel free to talk to them as well about our technology. They're very good partners. And then also new, we can't really talk too much about it yet, but we have a large molder with a heavy presence in the medical industry that has just picked up our machine as well. And it took delivery. They'll be taking delivery over here, I think, before end of the month. So there's a lot of traction going on there. People start to realize that the affordability and the performance that they can get with this technology really opens up more doors to them. Future of tooling. So in my opinion, where things are going, right? In my head, I'm always trying to think farther out. And the sad part is, if you see the picture on the right, I was doing that in 2016, right? This is 2024. So this is, I gotta add up, 6 years later. Well, no, 8 years later. Oh my gosh. Might actually go back for math. So 8 years later, and the tech and people have, it has still not gotten to where I think it could go in future. And you're going to see a lot of stuff coming out this year in regard to lightweighting and hollow inserts, a lot of partnerships we're doing. And it's really cool stuff. Please keep tuned in. You're going to see some really cool stuff coming out here, whether it be at LinkedIn or at the shows. Cool stuff, but I'll stop that in a minute. But so the far left, you see what's called copper alloy parts. We currently print a copper alloy. No, it's not copper beryllium. I know it's everybody's asking for. We're not printing that. But the hardness isn't quite there yet for our copper alloy parts, but it's something I want to explore deeper, right? Knowing that you could pull heat out fairly quick with the copper alloys, everybody knows. But I want to play around with what the kind of hardness we can get out of it, where it can go, and what the limitations of it are going to be. But so look for that, and again, more towards the end of the year, along with Xact venting. So back in 2015, I was doing this. So everybody's familiar with Cor-x material. So basically, that's a speaker grill insert there, right? You're trying to draw that gas out, or the gas traps from the molding process. Cor-x get used a lot in the industry. Back in 2014, 2015, I was actually printing 90% density parts, so you can actually hook up a vacuum to it and draw the air through as you're molding in. So to mimic Cor-x, but you can print it. So you don't have to worry about secondary machining options, or, well, let me phrase that. So to go back in and EDM all those surface finishes on there, you can actually just print it. So really cool stuff. So we're working on the parameters on that, and that'll be probably end of Q2, beginning of Q3 to start releasing that stuff in the parameters. Die casting. This is on our radar. We know it exists. We know we've got to get into it. But just for everybody's terminology, so there's materials out there called Divar, which Udahome makes. We're actively looking at it. It requires a bed temperature about 250, 200 to 250 C, so quite a high bed temperature. There's only about a handful of machines in the world that can do that. We know that, and we're going to be working on our machine to adjust it to be able to compensate for that down the road. So again, we can't build this ship without everybody else kind of giving feedback and what the world really needs. Then we can kind of tailor and move accordingly, which is great about working for a company like this. And then the last point on there on the right about lightweighting and hollow inserts, right? That part initially was had a baffle in it, and then I redesigned it with conformal cooling. So with the baffle, it was about a 60-second cycle time. I redesigned it with conformal cooling. I got the cycle time down to 45 seconds. Now, what was being molded was a clear polycarbonate part for the medical industry. We had little threads on the top. But I want to point out that by thinking things differently, I took what was a conformal cooled insert. It took 197 hours to print at a price just under $5,000, and got it down to a 92-hour print that took about, it was about a 92-hour print printing it hollow. And the thought was that I got to the guys over at Inspire Software and said, hey, how much, if I got 18,000 PSI of plastic pressure on here, how thick does the wall really need to be? Do I really need a solid chunk? Turns out you don't. Oh, I needed 4 mils of wall stock, really? So I went 5 mils of wall stock because, belts and suspenders, why not? Go a little bit thicker because that's what we do. But then I added liquid CO2 to it to help cool it down, which liquid CO2 does a phase change when it goes from liquid to, as soon as it hits atmosphere, it rapidly expands and becomes like negative 109 degrees Fahrenheit. So I was actually able to take the cycle time from the conformal cooled at 40 seconds down to 35 seconds. So I knocked another 5 seconds off that cycle time by doing something completely different. And the cool thing about the liquid CO2 is it evaporates. So you don't have to worry about water residue or rusting. So it's some cool stuff. But again, just trying to show that this is where I think there's a lot more. You've probably seen a post from Martin from Arberg last week that was talking about, it had a mold insert that I think he said looked like a spaceship. Again, the future is coming, but if we just got to open our minds a little bit and be able to adopt it. Speaking of lightweighting, this mold insert here, I know I'm getting close in time, I'll try to wrap this up. The solid versus lightweighting. So you see the part on the left, just about 1,100 cc's, and the part on the right with lightweighting is about just under 900 cc's. Now, this could be lightweighted more, it could be optimized a little bit differently, but just want to point out that that much reduction in material, but also that much reduction in weight as you're opening and closing the press, right? If I've got less weight I'm opening and closing the press with, I have less energy I'm using to open and close that press, which means I'm using less energy, right? So if you take that times, if I've got 50 injection molding machines in my shop and I reduce the energy on each one of those machines, that could have a much larger global impact, right? By reducing the metal powder, something as simple as that. Why put the material there if you don't need it, right? So that's, again, I think where we really need to go. So to wrap it up, and I'll open it up for questions, please come see us at trade shows, reach out to us. We'll be at RSNA in Chicago, which is medical. We'll be at NPE, booth number 25196, which I think still shows it as a Cimquest booth. So thank you, Cimquest, for allowing us to nudge in and take over your booth. We'll be at Rapid, IMTS, Lab Day, Formnext. So please, open the, come see us, come talk to us, and come see parts you can hold in your hand. And by the way, by NPE, we should have that A1 finish on some low contour crown parts. So you can, I'll have a little microscope there. You can get under it and check it out with your naked eye. So thank you all.
Hey, Scott, I'm starting to see some of the questions that are coming in.
Okay.
Yes.
Can you see those on your side?
I can go ahead and read them out to you guys if you'd like. So
yes, please.
Great.
First one we have coming in was, do you see potential in multi-material 3D printing?
Great question. I've been looking into that with a company called Aerosint. They do a lot of stuff with the multi-material. I think there's potential for it. We are not able to do that with our technology, but I do see the multi-material as taking some stronghold, putting copper in some certain areas there, and then printing with the steel in other areas so you can get the hardness and also be able to pull the heat out. But to be honest, I think that's where, like, I'm going to go off on a tangent here, but it'll make sense. So I've had a lot of people ask me about printing aluminum tooling, right? Hey, I just want to print aluminum tooling and that gets it done. But really, you can machine aluminum fairly quick. And the conformal cooling doesn't have a benefit for that, right? So I think the multi-materials kind of go along the same track. You can do it, you can pull heat out of certain areas, but if you can put conformal cooling up inside those areas and pull the heat out, do you really need multi-material? Not saying I have I'm not saying I have the answer for that, but just kind of throwing that question back out there. So good question.
All right. And some of these questions may go into things that were discussed, but some people drop in and out. So if you could just sort of reiterate some ideas. One person said, Scott, why are you with Xact Metal with your extensive tooling background?
So I cut my teeth on laser powder bed fusion back in 2012. I've been around the world, so let's call it, so to speak, with a lot of other technologies, and realized that about 4 years ago, I actually approached, I met Juan Mario and Dave at a booth at a plastic show, and realized that, or the PT Expo, and realized that the machine price point, that I could put one of these in my garage and start printing mold inserts out of my garage for people. It's a good technology that has a good surface finish, and it's affordable. So based on that, I'm like, okay, here's where this technology, I'm like, I either need to get one of these things, or I need to be able to help kind of finish what I started back in 2016 with going after lightweighting. I think that there's a huge market potential for that, to be able to get people to adopt. So long story short, I've gone back to where I cut my teeth on a technology that I know is tried and true and works.
Okay, next one we have is, and this is very general, but why would you use additive manufacturing for tooling? And that's pretty much goes into this whole presentation, but.
Yeah. Hopefully by the end of my presentation, that answered the question for you. If not, I'm sorry. I don't know. Maybe I should have done a better job. Feel free to pull me aside at any conference and talk. That's a tough one, right? So why would you? Why wouldn't you? Right? So think of it this way. So the EDM, and I meant to say this earlier and I forgot, so I'm going to beat it right now. Hopefully everybody's still online. So the EDM did not replace the CNC machine, right? Think of it 30, 35 years ago, 40 years ago, and see it when EDM came out, people were afraid. People said, oh, it's new technology. It's never going to replace my CNC machine. But it's another tool in your toolbox to be able to get the job done, right? Additive manufacturing is that same thing, like EDM was. It's another tool in your toolbox to get the job done. Some stuff's a fit for it, some stuff's not. Straightforward. If you're making mold plaques for testing, 3D printing is really, there's no point, right? You can machine it faster with standard technology. But the idea is it's another tool in your toolbox to get something done, and you can do with some good materials on it. So to me, that's kind of, it's coming. So either you jump on board or you get left behind. Sorry,
All right.
I'm straight and honest with it. So
No, I appreciate it.
yeah.
Okay. Another one from the chat is, any demonstrated benefit with hot isostatic pressing of printed Cor-x?
I will have to loop in Udahome for that. I have not. I have done the hip process with other M300 parts, but not with the Cor-x yet. According to them, with the printing process that we've got and what we've done, the printing is 99. So our parts, M300, stainless steel, Cor-x, whatever the material is, 99.9% dense. So there's not a whole lot left to hip to take that out and add the shrinkage to it. There's not a whole lot left to shrink and compress that together. So the fact that you can, as printed, you can hand it over to a polisher and get an A1 finish on it, pretty much means you're pretty solid, and there's no reason to hip at that point, if that makes sense.
Great. Okay, we have a couple more. So where do you see the tooling in additive manufacturing market in the next 10 years or so?
Everywhere. Honestly, I think that everybody's going to have one, but it all comes down to the price point and how easy it is to adopt and how easy it is to train people to learn how to use it, right? Our machine, and I'm not making jokes here, but like talking with Dana, like she said the other day, she goes, even I can operate it, right? So it's so simple to use it almost it's like, why not? Why wouldn't you want to add it to your arsenal to be able to make more stuff, right? So as far as tooling 10 years out, it could be more multi-materials at that point. It could be more engineered grade materials. So right now what we say is standard tooling materials are going to be the next thing that's going to happen over the next, probably I'd say 4 years. But looking 10 years out, it could be, think of like engineered grade materials. So like right now, if you look at the plastics industry, you've got your PEEKs, you've got your Altums, you've got your Torlons, you've got a lot of engineered grade plastic materials coming out that they're focused on a solution. And I think that where Metal AM is going to go is down that same path. You're going to develop more materials. There's probably, I can remember being a few years ago at a show, and there was maybe 2 or 3 powder companies there. Now there's a dozen metal powder companies there. So more people are going on board. So I think that focused materials, engineer grade materials, if you want to call it that, I think are going to be where the future is going to go. Just my opinion.
All right. We have one question left that we'll wrap up on. This one's really hard, Scott. So good luck. But their question is,
Of course.
yes, it is. Where do I get one of those rhino paintings?
Thank you. Thank you. I believe that was a Marshall special. I think around the house we got a tiger, giraffe, and a rhino, and I'm a big rhinoceros fan, so love it. That's a perfect way to end this.
All right. So thank you
Thank
so
you,
much,
Carol.
Scott and Joe and all the attendees for joining. We will be sending out the recording to those who attended and those who didn't, as well as sharing it on our YouTube channel and our website. So if you weren't able to see it, you probably wouldn't be hearing me say this right now. But everyone will be able to find it. And if your friends are interested, you can send them the link. So thank you so much. Thank you guys. Have a great day.
Thanks,
Bye-bye.
everybody. Have a good one.